Maybe you wonder, where are the new ideas coming from if you apply research in graph neural network? And I would like to argue the case that it is from physics. That maybe if you start fresh in artificial intelligence, you should study physics. So let's have a look at this. Now, I want to show you that here on top you have a simple example. You have a pipe, and one end of the pipe we increase the temperature. Now, in physics, in theoretical physics, we have the heat diffusion equation, and you see it here written out in full beauty. It is a partial differential equation, and you see here the beautiful interplay between mathematics and theoretical physics. But this you can apply to graph neural network. Let me show you how. Imagine we have another tube, and now it's not that we put heat on one end of the tube and look at the heat diffusion across the pipe, but let's say we have a tube full of water and we put in a drop of color and we watch how the color transports itself through the tube more or less, and how the physics describe this. Now, this is equivalent to something in a graph neural network. And let's say we have a topic where we have nodes in a graph. And as you can see here, this is a graph, and we have here something with 3 nodes have given a specific feature. Let's say it's 18. And we want to have now the qualifier of the missing node. Now, how can we do this? And I would like to show you that current AI research, they do it because they rely heavily on theoretical physics and the mathematics that was discovered hundreds of years ago, and they applied now on new diffusion mechanisms in graph neural network. Because if, for example, you take here all the average sum of all the closest neighbor, you find a solution. So let's have a look at a typical model. We have a 2-layer graph convolutional network model. And you see here about the node embedding Z. This is the beautiful famous formula here in blue. And of course, our sigma denotes an activation function. For example, a ReLU function. Now, the 2 inputs to this model are the normalized adjacency matrix A, which encodes the graph structure, and the feature matrix X, which contains as row the node feature vectors. And it outputs the node embedding set that we're looking for. Now, each layer of the graph convolutional network performs a node-wise feature transformation parameterized by the learnable matrices W1 and W2, and then propagates the transform feature vectors to the neighbor nodes. But in real-world application, we have a different situation, because the feature matrix has missing values, and most existing graph neural network models cannot directly be applied to this case, because some of our nodes have missing values. So the task for us is, how can we kind of reconstruct those missing values? Now, there is a beautiful article by grandfather Michael Bronstein, and of course he is presenting a new methodology he calls feature propagation for learning on graphs with missing node features. And just want to show you this, and this article appeared in February 2022 in Towards Data Science. Here you have the link to the HTTPS. But interestingly is, what is the main idea behind this? And I would like to argue in this video that there's a lot of physics from theoretical physics flowing in now in this particular approach of feature propagation in graph neural networks. Let's have a look in detail. And as you can see here is the original archive preprint from May 2022, published by Emanuele Rossi and his colleagues from Twitter and Imperial College London and University of Oxford. And there are 2 very important sentences I want to show you. Because for handling the missing features in graph machine learning application, they do a minimization of a specific Dirichlet energy, which leads to a diffusion type differential equation on the graph. So we use the knowledge from theoretical physics on diffusion type differential equation, and we apply it directly on the graph. And then, of course, you cannot go for a pure analytical solution, but you want to have a computer simulation, so you have to find discrete values and how you can optimize it for coding. So they found a solution to produce simple, fast, and a scalable algorithm, which then they called feature propagation. And I would like to show you a little bit of physics behind the idea and how important it is not just to have an understanding of statistics, but the knowledge of physics is so important. So let's start. The level that the features are similar can be quantified using a specific energy, and the quadratic form measuring the difference between the feature of a node and the average of its neighbor is of importance here. Now, the gradient flow, and you remember the gradient descent mechanism already in back propagation. Now here we have a gradient flow of an energy is the graph heat diffusion equation with the known features used as boundary conditions. So we have a classical system with specified boundary conditions. And here, this is from the archive preprint, the original formula. And as you can see, the evolution of the missing features can be regarded as a heat diffusion equation, physics, with a constant heat source. This is Laplace x coming from the boundary nodes, the known nodes, the ground truth nodes, where we have the information on the values. But you might say, wait, in models just as GCN and Graph Sage, where node embeddings are computed as weighted average of neighbor embeddings, why do we not use the same methodology here and just take the average of neighbors? Well, things are not so simple as you might think. Because let's look at the original preprint, and they say why the simple neighborhood averaging performs competitively. Let us assume we have a single feature channel, and this feature has to be very similar over the graph. So when a node has enough neighbors around itself, the average of their features is a good estimation for the feature of the missing node, of the node where we have the missing feature. However, as the rate of the missing features increases, the feature may be present for only a few neighbors. Imagine just maybe 2 nodes, or none at all, causing the estimate to have a higher variance. And now comes the beauty of this heat diffusion equation, because it allows information to travel longer distances in the graph by repeatedly multiplying itself by the diffusion matrix. And even if you do not observe the feature for any of the node neighbors, it is still possible to estimate it from the nodes further away. But be careful. This feature propagation methodology is designed for graphs with only one node type and only one edge type. And as you can see on the left side, there's of course the baseline problem, and they show in the preprint you can set the values to 0, no problem at all. And if you do it, it is simply to reduce the norm of the average embedding of all nodes. They argue, set it to 0, and then we start with our optimization problem. So let me summarize our findings. At the top, you can see here that we have the physical investigation from hundreds of years ago, from Laplace equations for steady state and then for the heat diffusion, heat transfer equation. Here, beautiful, and either you have temperature or you have dilution of some color in some medium like water. You can calculate it very clearly and even in an analytical solution. But if you ever wondered how you get the ideas to find new AI or graph-specific learning algorithms, well, look no further like theoretical physics, because those problems have been investigated for centuries, and the solution that they have found with the help of mathematics, and sometimes mathematics was developed especially for some physical problems. Now they take this knowledge and they apply it to graph neural network. And I think if you are interested in GNNs, do not forget, if you have the chance, study physics, study mathematics, because the future of artificial intelligence will rely heavily of the insights and of the knowledge transfer from theoretical physics and mathematics. Thank you.